Hello friends, in today's topic we will discuss on the amplifier which is constructed using a transistor in common emitter mode. In the diagram you can see there is a transistor and this type of transistor is NPN transistor, it is used here. The base to emitter voltage is the input voltage and connected to emitter side it is the output side. On the input side there is a signal Vi, it is connected, and this input signal is the input signal which is to be amplified using this circuit. After input signal there is a coupling capacitor which is connected here at the input side, and this coupling capacitor is used as a DC blocking capacitor, as the DC may changes the operating point of this transistor. Because of this DC, that operating point should not be changed, so that should be constant. So that DC from the previous stage of the amplifier has to be blocked. So that is why this blocking capacitor is used. This capacitor only passes the AC signals from the input stage. So this blocking capacitor, it is very necessary in the common emitter or any type of amplifier. There is a biasing battery VBB is connected here. You can see the potential difference is very less because at the input side only a forward bias is required. So that is why the voltage can be less. So only one cell it is connected here. There is a base resistor which is connected between the battery and the base to limit the base current. So this was about the input side. Now at the output side you can see collector, it is connected to the battery, and the battery voltage at the collector side it must be high because the output side should have high amplitude. So that is why at the output side the potential difference should be maximized. So to maximize it we need a higher potential battery here. There is a resistor which is connected between the battery and the collector. This is the collector resistor RC. In this circuit, the output voltage is in between the collector and emitter. At the output, you can see another capacitor is connected. So this capacitor is also a coupling capacitor. It also blocks DC. So as the only AC signals has to be appeared as an output. In this diagram, you can see the input side, that is base to emitter, it is forward bias, and the output side, that is collector to emitter side, it is reverse bias. Now let us take a look at the DC load line, how this DC load line is configured. Let us see. When there is no signal at the input side, this condition is called as quiescent condition, and the battery voltage VCC will produces a voltage drop across the collector resistor, and that can be calculated using the KVL equation. So at the output side we can express the KVL equation as VCC equal to ICRC plus VCE. From this, if you take the collector current towards the left hand side, the equation will be like this. So IC equal to minus 1 upon RC into VCE plus VCC by RC. Now this equation is same as that of the equation for line, that is y equal to mx plus c. Now the slope of this line can be expressed as m equal to minus 1 upon rc, and the intercept on y axis will be c equal to vcc by rc. So in this way we can express this equation as a expression for the straight line. The straight line is nothing but the DC load line. So this is the equation for the DC load line. Now DC load line can be plotted on the output characteristics. Now output characteristics is nothing but a graph between the collector to emitter voltage versus the collector current. So collector current, it is taken on the y-axis, and the collector to emitter voltage, it is taken on the x-axis at VC equal to VCC and IC equal to 0. This point, let us express it this point as A point. and Vc equal to 0 and Ic equal to Vcc by Rc, let us call this point as B. Now these are the points which has the maximum value of voltage on collector to emitter voltage axis is A, and the collector current, that is the x axis, on which the highest value of current, that is represented by the point B. Now the line joining these 2 points A and B is nothing but the DC load line. Now in the graph you can see there are various base currents, and the graph is plotted for various base currents. Let the current is IB0, that is the least current applied at the base, so it will be plotted by a line IB0. If the base current is increased, there will be another line. Let us represent it by IB1, IB2, IB3, IB4 and so on. Now the line which intercepts the graph of base current and the DC load line, that point of intersection is called as the operating point, or they may be called as the quiescent point. Now all the graphs of base current on the DC load line, wherever they intersects the DC load line, all the points they are called as the operating point. Now for the faithful application, we need this operating point should be set in the middle of the DC load line. So in the diagram you can see that the base current IB2, that intersection of DC load line, that point is in the middle of DC load line. So this operating point will be in the middle of the DC load line. Now the region where this operating point is to set is called as the active region. So for operating as an amplifier, we need this operating point should lie in between the active region. So this is how amplification is done using the transistor in common emitter mode. So this is the basic CE amplifier, which is used to amplify the lower strength signal to higher amplitude signals.